The last topic that's on the exam, the only thing we haven't seen yet, is this normal approximation to the binomial distribution. So it turns out our binomial distribution, well, some things happen when our sample size gets large. So I have open here StatCrunch with an applet that's going to show us what happens if we flip 10 coins with a probability of heads equal to 0.5. Well, if we do this one time, it actually shows us here are the 10 coins that were flipped. There were 6 heads. And it's going to poop out one little time that this happened. If we do this 5 times, you're going to see it's actually flipping coins and counting up the number of heads for us. And we could keep doing this. We could watch it poop these things out again. Whoa, a lot of 5s in a row. And we could actually say, let's just do that 1,000 times. Do it 1,000 more times. And we're starting to see, let me bring up my Windows ink screen sketch. We're starting to see this shape, right? We know that there's a mean of our binomial distribution, which is NP, which in this case is 10 times 0.5 or 5. And, well, that's exactly where the mean of our distribution is. And as we move away from that mean, everything becomes less and less likely in this nice symmetric pattern. So as long as our sample size is big enough, there's almost a normal distribution happening here. So if you look at our notes, it tells us that we actually have a rule for what is sufficiently large. And our rule is that n times p has to be greater than or equal to 10, and n times q has to be greater than or equal to 10. So that previous example where np was 5 is not big enough. We actually need our np to be at least 10. So if we go back and try another example, say, okay, I have this. Let me change my options. And this time, instead of looking at 10 coins, maybe let's look at, sorry, I have to bring up a keyboard. Let's look at 100 times. Make that a 0. You really want to make that a smiley face? All right, so if we compute this, now you can see on my little output here, number of heads, we have a 30 to 70 range, 50 is in the middle because that's our expected number, right? So if I do this one time, it tells me that there were 53 heads. And then it's going to pop, boop, a little number out at 53. I could do this 5 times and watch as it does this for us. Sometimes we get less than 50, sometimes we get more than 50. If we do it 1,000 times, 1,000 more times, you can start seeing, again, what we see even more. Oh, right, cancel. I'm not drawing my drawing pad. We can see even more so that kind of bell curve starting to happen. Before we had unimodal and symmetric, now we have a nice bell shape starting to form. So what is this greater than or equal to 10 business about? Well, it's partially about having a large enough sample that we can start getting this bell shape, that we can have this kind of inflection point that's going on within this. If you don't know what that means, don't worry. But the other part is, let's go back and change our options again here. If my probability of heads was something very low, let's say, I keep forgetting I don't have a way to write. Let's say our probability of heads was 0.05. Cool. So if it's 0.05, that means our expected number, right, our NP, would only be 5. 5% of 100 is just 5. So if I do this, now our expectation, right, is NP 5 heads. We do this once, we get out 4 heads. Okay, pops out our 4, kind of where we expected. We do this 5 times, we get a lot of values around that 4 around the 5 we expected. We do this 1,000 times, 1,000 more times. Now we're not seeing that normal distribution. We're starting to see a little bit of a right skew, right? We're starting to see a little bit of that tail off to the right. So this is why we need that NP and NQ to be greater than or equal to 10. Because if that's true, we'll have enough space that we're not butting up against an edge like this. So we really need this to be true. In fact, let me just do one more example of this before we move on. If I change this again, this time making NP something that happens very often, so I can change this to 0.99. Now, if 99% of the time we get heads and there's 100 coins, we expect 99 heads. So if we flip one coin, sure enough, we get 98, very close to our 99 we expected. We do this 5 times. Again, we're going to see values very close to 99. And we do it 1,000 times, 1,000 more times. Now it's almost impossible to get away from this. We actually have a very much of a right skew, or a left skew, right? Most of our data is at 99 or 100 because we're butting up against that edge. So that is what this rule of thumb, this NP and NQ being greater than or equal to 10, is that our number of successes and number of failures have to be far enough away from those edges that we are able to have that unimodal symmetric shape that we need with our normal distribution. So if all that is true, then we can actually use the normal distribution to approximate probabilities from the binomial. So we're going to go ahead and do this for one example. I'll take a moment and pause the video and start a new one, so that way you can take a break.